Good morning friends. Last we discussed about the binding energy and binding energy per nucleon. Right? The binding energy, that means what is the mass defect of the nucleus. Right? Delta M is equal to, already we know the equation of the mass defect. According to the Einstein's mass energy relation, the binding energy is delta M into C square. This binding energy is divided by number of nucleon in a nucleus, that is known as the binding energy per nucleon. Now, today we are going to discuss about what is the relation of binding energy per nucleon versus atomic mass number. That means the binding energy of nucleon for different element. What is the value of binding energy per nucleon? For that purpose, we do the graph of binding energy per nucleon versus atomic mass number. The graph is shown in the figure. On the y-axis, we consider the binding energy per nucleon in mega electron volt, while on the x-axis, we consider the atomic mass number A of the different element. Right? Now, what are the notable points of this graph? From the graph, it is shown that the light nuclei, that means the nuclei having the atomic mass number is less than 30. The binding energy is less than 8 MeV. While the same thing, the nuclei having the atomic mass number is more than 170, approximate 170. The binding energy per nucleon is also less than 8 MeV. While from the graph, the binding energy per nucleon for iron Fe, atomic mass number is 56, is the highest value of binding energy per nucleon, EBN. Clear? Okay. So here we are going to discuss this thing. While the nuclei of middle range, that means the atomic mass number is greater than 30 and below the 170, the binding energy per nucleon almost remain constant. For this part, the binding energy, the change in binding energy per nucleon is very less compared to the light nuclei and heavy nuclei. So these are the notable points of the graph. Okay, we discuss it only. This graph is only for information. Sometimes the 1 marks objective MCQ question may be asked in board exam or the NET. For that purpose, the question is that the graph of average binding energy per nucleon against atomic mass number A and write notable points. The graph of average binding energy per nucleon in MeV versus atomic mass number A is shown in the figure. Clear? Okay. Now, notable points of the graph. First point is that the binding energy per nucleon, EBN, is constant and it is independent of the atomic mass number A for nuclei of middle mass number 30 less than 8 less than 170. Just we discussed it. The binding energy per nucleon of the atom having the atomic mass number is greater than 30 and less than 170 is almost constant. For this nuclei, the binding energy per nucleon is almost constant. Practically, it is independent of atomic mass number. Clear? So that is our first point. Okay. Now, the value of maximum binding energy per nucleon EBN is 8.75 MeV per nucleon. That is for iron Fe having the atomic mass number A is equal to 56. From the graph, for this atom iron having the atomic mass number A is equal to 56, the binding energy per nucleon is maximum and its value is 8.75 0.75 MeV per nucleon. For iron, binding energy per nucleon is maximum. While the value of binding energy for atomic mass number A is equal to 238 is 7.6 MeV per nucleon. The atom having the binding energy per nucleon is 238. This there is only 7.6 MeV. 7.6 MeV per nucleon. It means for the heavy nuclei having the binding energy per heavy nuclei, the binding energy per nucleon is also less. Highest or the maximum value of binding energy per nucleon for Fe iron atom. Having the atomic mass number is 56. While for the heavy nucleus, having the atomic mass number is 238. The binding energy per nucleon is only 7.6 MeV per nucleon. Okay. Therefore, the binding energy is lower for both. Like nuclei, having the atomic mass number is less than 30, and the heavy nuclei having the atomic mass number is greater than 170. It means the binding energy per nucleon for this range atom having the atomic mass number is less than 30, and for this nuclei having the atomic mass number is greater than 170. For both light and heavy nucleus, the binding energy per nucleon is less. Okay. Now, from the graph, the binding energy of 1H2 is lowest and for iron Fe is highest. Now, this 1H2, the binding energy per nucleon is minimum, while for the iron, the binding energy per nucleon is maximum. 1H2 deuterium, the binding energy per nucleon is maximum, is lowest, while for iron, the binding energy per nucleon is maximum. So sometimes a 1 marks question is asked from here. For which of the following atoms the binding energy per nucleon is lowest or the highest? For highest, Fe iron. For lowest, deuterium 1H2. Now, the ratio of the neutron and proton is required to be 1:1 for the stability of a light nucleus. Right? Whereas for the heavy nucleus, this ratio increases to 3:2. For the 3:2. Now listen, how the nucleus becomes stable. Already we know that inside the nucleus, the chargeless neutron and positively charged proton are present. For the light nuclei, the number of proton and number of neutron are same. For light nuclei. So the light nuclei having the same number of proton and same number of the neutron. So these nuclei are stable. But for the heavy nuclei, for the stability of the nucleus, the number of the neutron must be greater than the proton. Must be greater than the proton. Because already we discussed about the nuclear forces between the neutron-neutron, neutron-proton and proton-proton. The force of attraction is exerted between them, and due to that reason, the chargeless neutron and positively charged proton are combined together in the small central region of an atom that is known as the nucleus. For the stability of the heavy nuclei, the number of the neutron required is more than the number of proton, and this ratio is 3:2. While for the light nuclei, for stable nuclei, this ratio is only 1:1. So keep in mind that for the light nucleus, for the stability, the ratio of number of neutron to the proton is 1:1. While for the heavy nuclei, for stability, this ratio, that means the ratio of number of neutron to the number of proton is 3/2, or the 3:2. Right? Okay. Now the next question is that, what is the conclusion of the graph of atomic mass number, or the binding energy per nucleon versus atomic mass number? Right? What is the conclusion? Already we discussed about the 3 point. One point is that the binding energy per nucleon for the ion Fe is maximum. Right? Second is that the binding energy per nucleon of the middle order nucleus having the atomic mass number greater than 30 and less than 170 is almost constant. And third, we discussed about that the ratio of number of neutrons to the number of protons for the light nuclei is 1:1. For heavy nuclei, that is increased to 3:1, 3:2. That means the 3/2. Now, what are the conclusions for the for the graph of binding energy per nucleon versus atomic mass number? So, conclusions are: first is the nuclear force is attractive and sufficiently strong to produce the binding energy per nucleon. Inside the nucleus, we know that there is the nucleus, there is the atom. Inside the nucleus, the proton, positive charge proton and chargeless neutron are present. Here, the force of attraction is exerted between the unlike charges. But here, neutron is the chargeless, proton is the positively charged. So, if the heavy nuclei, so more than one proton are present, between the two protons the force of repulsion is exerted between them. Yes, the repulsion force exerted between the proton in a heavy nucleus. Why? The question is that, why the proton and neutron are bounded in small central region of an atom, that means inside the nucleus. That means the one strong force of attractive exerted on this proton and this neutron, which force bound the proton and neutron in the nucleus. Right? Therefore, the nuclear force must be attractive and sufficiently strong to produce the binding energy per nucleon. So, in spite of the repulsion force exerted between the proton inside the nucleus, the one strong force of attractive must be act between the proton, between the proton-neutron, and between the neutron-neutron, which bound the proton and neutron in small central region, that means inside the nucleus. And this force is known as the nuclear force. And this nuclear force of attraction produce the binding energy per nucleon. Second conclusion is that because of the short range nuclear force, the value of binding energy per nucleon in the nucleus heavy, the atomic mass number is greater than 30 and less than 170 area is almost constant. Again, because of the short range nuclear force. Nuclear force is attractive force. And this attractive force is only exerted up to the certain femtometer. 1 femtometer is equal to 10⁻⁻15 meter. And due to that reason, the value of the binding energy per nucleon for the middle area or the middle range nuclei having the atomic mass number is greater than 30 and less than 170 almost constant. Right? For the constant binding energy of the nuclei having the atomic mass number greater than 30 and less than 170, the short-range nuclear forces are responsible. What is the reason? In large nucleus, the force on nucleus is only due to its neighboring other nucleon, but it cannot be exert a force on a far nucleon. So inside the nucleus, suppose there is the nucleus. In a nucleus, the number of the proton, and there is the heavy nucleus. So as you consider, there is the nucleon. So either the force of attraction is exerted on this nucleon by its surrounding neighboring nucleon. It cannot apply the force of repulsion or the force of attraction on the far away nucleon. Far away. Now what is the nucleon? Nucleon is either proton or the neutron. Because for the nucleus, for the nuclear forces, there is no difference between the proton and neutron. According to the nuclear forces, the strong force of attraction exerted between the proton or proton-neutron or neutron-neutron. In spite of, there is no charge of a neutron. And therefore, the proton and neutron commonly known as the nucleon. The proton and neutron is commonly known as nucleon. So nucleon, that means either the proton or the neutron. Inside the nucleus, the force of attraction is exerted on any nucleon due to its surrounding neighboring other nucleon. But it cannot exert a force on the far nucleon. If a nucleon has a maximum P number of neighboring nucleon within the range of the nuclear force, so its binding energy would be proportional to P. Now, the one nucleon, if it has the P number of small p, number of the nucleon of its neighboring, therefore, the binding energy would be proportional to the number of nucleon surrounding this nucleon. Therefore, the binding energy of the nucleus is P into K. K is the constant having the dimension of energy. Just the earlier paragraph we discussed about that the force on nucleon is only due to the neighboring other nuclei. Only what are the nucleon are in neighboring of a given nucleon can apply the force of attraction on the nucleon, while the far nucleon cannot apply the force on this nucleon. So this nucleon, only this neighboring nucleon can apply the force, while the far nucleon cannot apply the force. Right? If a nucleon has the maximum number of the nucleon is P, therefore the binding energy would be proportional to P. And the binding energy of the nucleus is Pk. K is the constant having the dimension of energy. Okay. If A increases by adding the nucleons, it will not change the binding energy of the nucleon inside. Thus, the most of the nucleon in a large nucleus reside inside it and not on the surface. Not on the surface. Therefore, the change in binding energy per nucleon would be very small. So what it says that if there is a heavy nuclei, yes, we add the one or two nucleon in this nucleus. So what's happened? So this nucleon, added nucleon cannot occupy the space between the two nucleon in its neighboring. Therefore, the binding energy per nucleon is not changed, almost remain constant. Again, if A increases by adding the nucleon, it will not change the binding energy of nucleon inside. Let's we add the nucleon in a nucleus. So what's happened? These nucleons are on the surface, not inside. Therefore, the binding energy is not changed. Therefore, in large nucleus, the most of nuclei reside inside it, not on the surface. So, adding nucleon cannot occupy the space inside the neighboring nucleon. It is only made on the surface. So, the force does not change. Therefore, the binding energy per nucleon also not change. Therefore, the change in binding energy per nucleon is also small. Such property of a given nucleon is referred as saturation property of the nuclear forces. In case of a heavy nucleus, such property, that means by adding the extra nucleon in a nucleus, the binding energy, change in binding energy per nucleon is almost very small. So that is remain constant, and this property is known as the saturation property of nuclear forces. Clear? Therefore, the middle range area of element, the binding energy per nucleon is almost remain constant. Or in other words, the binding energy per nucleon for the nucleus having the atomic mass number greater than 30 and less than 170 is almost constant. Now the next is the binding energy per nucleon of nucleus. A is equal to 240 is less than the value of the nucleus having the A is equal to 120. What it says that? The nucleus having the atomic mass number A is equal to 240. Its binding energy is less than the nucleus having the atomic mass number A is equal to 120. What is the reason? If the nucleus of A is equal to 240 bags divided into two A120 nuclei, right? The nucleus gets the more tightly bound, and this implies the energy would be released in this process. When the heavy nucleus of A is equal to 240 is divided into the two nucleus of A is equal to 120. So in that case, the nucleus are more tightly bound in both of this nucleon. Again, if the nucleus of atomic mass number A is equal to 240 divided into the two A is equal to 120 nuclei, the nucleus of A120 the more tightly bound. This implies that the energy would be released in this process, and this process is known as the nuclear fission process. Nuclear fission process. Nuclear fission process, that means when the heavy nuclei is get divided into the small nuclei, the energy would be released. And this process is known as the nuclear fission process. And that is the principle of atomic bomb. When the atomic bomb is blast, so large amount of the energy is released. Again, when the heavy nucleus of atomic mass number A is equal to 240 breaks into 2A is equal to 120 nuclei, the nucleus get the more tightly bound, and this implies that the energy would be released in this process. And this process is known as the nuclear fission process. Nuclear fission process is the principle of the atomic bomb. Is the principle of atomic bomb. Now the similar way, if the two like nuclei having the atomic mass number A is less than 10, join to form the heavy nucleus. Join to form the heavy nucleus. The binding energy of the fused heavy nuclei is more than the binding energy of the light nuclei. So what it says that the two light nuclei are combined to form the heavy nuclei. So the binding energy of the fused nuclei is more than the binding energy per nucleon for the light nuclei. And this heavy nuclei is more tightly bound than the light nuclei. So this fused or the produced nuclei is tightly bound than these two light nuclei. The energy produced in this process is also known as the nuclear fusion process. The energy is produced in this process, and this process is known as the nuclear fusion process. Here the two light nuclei are joined to form the heavy nuclei. So heavy nuclei, that means the fused nuclei, is tightly bound compared to the light nuclei. So here the energy is also released, and this process is known as the nuclear fusion process. And the principle of the hydrogen bomb and also energy source of the sun, it works on the base of the nuclear fusion process. So in this chapter we have to discuss about the nuclear fission and nuclear fusion process. When the heavy nuclei is divided into the two light nuclei, the energy is released, and this process is known as the nuclear fission. When the two light nuclei are combined or joined to form the heavy nuclei, so energy is also released, and this process is known as the nuclear fusion process. Nuclear fission process is the principle of the atomic bomb, while the nuclear fusion process is the principle of the hydrogen bomb and the source of the sun. How we get the energy from the sun. Clear? So these are the conclusion of the graph of the binding energy per nucleon versus atomic mass.